Okay, what's up, everybody? Welcome back to Stuff by Innovative Potential, part of the World by Innovative Potential. And I am brought to you by Innovative Potential. And I'm Jordache, got my haircut, and I'm sitting here with the second Joey thing, and we're gonna go over a kit I got from Freenove. It's an ultimate starter kit available on Amazon. It is an electronics kit. It gives you things like this, computer parts, and it gives you a really, I'm gonna say good. It's worthwhile. It's a worthwhile kit to introduce you to electronics and video games. Basically, it is going to take you from like 1945 electronic knowledge to probably, I guess I'll call it sort of about 1972-ish, kind of. But, it gets you in a position where you can build your own robot machine that is going to be able to do something repetitively and be able to it's gonna be able to provide you with like a new tool, for the show, sort of say. So that's sort of the way to think about it, way to approach electronics, because how do you, where does your video controller come from? So that's sort of the idea here. It gives you introductory to sort of like, this is to all of the components, I guess, on how to here's a little speaker, here's a little buzzer, here's a little speaker, here is an LCD grid. They also give you an LCD number, which is like a grid. They give you a whole bunch of these little buttons and light bulbs and switches that come with it. There's a servo motor, there's a regular motor, there's a battery motor, there's a whole bunch of resistors, a capacitor to a couple of flip switches. There's some neat little cool ones in here also that are like moisture, like the moisture temperature detectors. There is a keypad that you can go through a program. There is I like the sonar test. The sonar test was a good one. It's like a sonar radar where it bounces off sound and then it measures the sound wave coming back to it. So that was a pretty neat little thing. And the idea is sort of these are the parts and the components that you're gonna learn and have to learn how to use independently, so that you can build larger things. So if you want to build a robot or something, you have to know how, why are you using a transistor, or why are you using a light bulb, basically. Why are you doing what you're doing? And then there's a little soldering kit at the end. So sort of one of the projects is to build this battery and light bulb with a little button there. Right, okay. So the way I did this is I inverted the light bulb so that when you turn it on, the power source can reverse its polarity and activate the light bulb silently. Yeah. Or if you turn it around and you hit the buzzer, you can have you get like a little beeper on it. So if you want it muted or unmuted, you can kind of figure stuff out. It's really neat to play. Learned how to solder as well, so that's a good skill to have. You kind of know about these things growing up, but until you actually have to go in and use them, you do need hand-holding with some of this stuff, because it has gotten so much advanced lately. So like if you wanted to have like a little like toothbrush maker. You put one of these little motors in it, and it'll vibrate and oscillate for your toothbrush head. And yeah, Freenove is just freenove.com, and they have a whole bunch of like a ton of kits on there. There's kits, there's robot kits, there's Arduino kits, programming, sort of basically everything you want in a kit to be able to do your own, basically do it Joey or chemotherapeutic attention. So what we're doing with the CGPs now, so this evening is all sort of innovative engineering time here. This was a hard one because you got to be like what is the engineering persona, and they do well to get. It's like a 300-page instruction manual on like 25 different sort of sit down. This is Arduino. This is how Arduino works. Here's how to call a library. Here's how to do a basic program in it. And here's how to wire a circuit. Here's how to use a breadboard. They give you a breadboard. They give you the Arduino board, the breadboard, some basic types of connectors. Batteries not included. And just kind of have you build everything from there, and sort of just leave the rest up to you. The rest up to you is just sort of why are you making stuff? You get your connectors, bundle the connectors, and learn how to make a piece of electronic equipment that you can program, or that may or may not have a program, because the equipment has gotten very cheap, and the amount of education you get in a $50 kit is insane. There are limits on it, in the sense that the complexity of the program is dependent on like what you want to use, but I can get all of this. You can build the Joey with the kit itself. You just need the electrochemical cell. So that's sort of like how accessible this is for basic technology pieces that have been around since 1972. The Arduino is something different. I think it was like really started to be pushed in about like 2010ish. Because I remember in grad school back then, it was just kind of coming up on my radar, but I never really paid attention to the programming outside of like game macros and stuff. So that's sort of the everything about it. And going on from there, we're gonna make this all about the Joey, because that's what it's about. So the whole kit just fits in this like 6x6 unit, kind of basically about the size of the Joey. The whole kit fits in this here we go. This, it's unsponsored, but it's worth it. So this little electronics kit, it's like a little tackle box with electronic stuff for whatever you're building. It's 8 by 4ish, 8 by 4 by 2, Joey 6 by 6. So everything you need to like basically wire a Joey to do some component parts and pieces is available in this kit. It's $50, and you can sort of go from there and like make your own fuel cell. Yes, but no, but yes, but no, but you just got to keep that motor running. So that's sort of how that works. So the Joey was closest to the 16B or project in the a tutorial package, and 16B was the closest to it. It uses the Arduino board to power a, I'll just show you here, a small LED. So what I'm going to do is we're going to power the board up with the batteries. I preloaded it. So what this is doing here, switch it over just a little bit. So what that mess of spaghetti wires there is basically doing is the board is powered by the 9-volt battery, which then powers the LED through the 5-volt pin on the Arduino. And then the rest of the circuit, I've built a small circuit with an on-off switch for the LCD for the whole thing, except for the board. That's just because that's how it works. You have to like put the on-off switch in front of the battery, but the components, it's just easier this way. I just unplug the battery. There's an on-off switch for the LED. There's an on-off switch with a light bulb to show that the electrochemical cell is on. And then what I do to fail safe is I introduce manually a small LED light bulb saying on the back side of the electrochemical cell there is confirmation that the cell does actually have power going through it in some way, shape, or form. So there's more redundancy and control to put into this than I probably actually already have used. But since this is now intended as a standalone sort of medical device, it needs the redundancy in there, and it also needs and it has some fail safes in the program. I'm going to get into that in a moment. So flipping the switch on, first thing that happens is the LED module lights up. It reads the time, the voltage, and the milliamps coming through the system. So with no actual load, you read the 5 volts and the 20 milliamps and the amount of time that it's been on. Because basically what you do, everything else is set up, and the last thing you do is turn this thing on. So it's going to give you an approximate time of ballpark of what it's doing. The Arduino set it up so that when it's connected to a PC, it will data log for you through the comms channel, but this isn't required for right now. So the next thing to do is we're still in this manually. So red to red, black to black. Finish up the rest of the in this case with the electrochemical cell here, the cathode is the cathode's the red and the anode's the black. But in the actual electrochemical cell, the way I have it kind of wired, the titanium is the red. So just keep that in mind. Red to black, so it actually changes color there. So that kind of gets changed when you get closer to like an actual node. We're going to be like manufacturing these without like mistakes or without the learning curve. Rather, the finalized product is sort of this. So then the next thing you do is you turn on the light switch for the electrochemical cell, and it gets power to the electrochemical cell. I don't fat finger it. And this little other green light bulb, what I typically do here is I just reset the Arduino. It'll reset the LED once everything's sort of on and active, and give a more accurate runtime of like how much time has elapsed on this machine. And with this little LED, I just verify myself. I just stick it in the circuit to make sure that it's operational. the idea is to have this whole thing. We're gonna like introduce a. There's a small kit I purchased from. Better get this right. There's a small kit that I purchased from a group down in Florida, and they were great, and they were able to provide a custom potentiostat, basically, to provide for me a 12 volt, anywhere from a 5 to 12 volt input and a 5 milliamp output, so that this whole system doesn't over deliver. So this 5 volt input is already delivering 13 milliamps to the system, and according to the book I used, it's probably perfect right about now, but according to the system that I had, we only need 5. We only need 5 milliamps going through the system. So it's already almost like 3 times as powerful as actually required. So when you put a drug into the system, you kind of have to start thinking about, well, there is a flow rate, there is a conversion time, there is a concentration factor, and there is an electrical factor to this that is all standardizable. So it really comes down to, is this the standard shape we're going to go with? Is this the standard shape? This is the standard shape that we have, but how is all the other stuff controlled? So basically right now, all the other stuff is controlled with a spigot. The idea is to build a small aperture frit so that the drip rate is physically controlled. Sort of like how they have the compressionals on the IB units already, but the idea here is that like the pinch of an hourglass, you're gonna just control how much speed goes through it. Light bulb go. Okay, so here you can see the light bulb. Bands on. Okay, so we're getting light from the blue light there. That's just basically confirmation that we're not like hoaxing you or whatever, that the power goes from the secondary switch through the electrochemical cell, and then then is able to, be grounded, and there's still electricity flow on the back end of the electrochemical cell, and that the reading that the Arduino is picking up is from the ground side of the circuit. So it's reading the back end of what's going on, and that's more important to note, because you read the front end, you never know what this thing is going to be doing, or if the cell fails for some reason. If the cell fails for some reason, you just sort of end up with like a ground situation. And so if you pull out one of the plugs, if anytime after operation there's a failure, this thing will reset back to 5 volts. And the light will switch off. So the green light will switch off. Like if this cell fails, the light's on. So that's why we have to put the other, like, the redundancy package is that this unit here, this circuit gets wired into this circuit, so that if it fails, this light comes on and the buzzer goes off. And that's sort of like that's a little bit more complicated, but for the independent user and product, sort of like once innovative potential puts us in a doctor's hands kind of thing, they need to have this sort of like, they need the buzzer installed into Joey to be able but we have to do better than that. We need the operational fail safes, because what we're doing is making a stranger aware of a piece of equipment they're not necessarily familiar with. The idea is the whole thing of innovative potential is like, no, this is like pure education. And that is not to say that the education can't be fun or anything. It's just more the work that you actually have to do is kind of keeps going. Here's your base workable. Everyone can have one now. There's a free version. Go assemble your own free version unit. The free version is loaded with inconveniences. This makes everything a little bit more convenient. Instead of having a desktop computer in a surgical suite, you now get something that fits on a charcuterie board. So that's not, crazy, horrible or anything. What fits on the charcuterie board now fits in this box. And then on top of that, that box can get compressed even further to basically being the size of by an 8x11 picture. So that's sort of the amount of tech, but that's sort of the issue. The technology's up and running. The drugs you are used in the hospital. So all of this is already done. Now it's the technology to get the manufacturing technology to get the actual technology to the point where you want to use it and it's convenient, not just know that you're obligated to use it, is kind of where the real sort of work comes in. There's it's only half the battle getting to the point where this exists, but the other half of the battle is getting this thing to the point where it can be sort of actually used in the field without having the so it's the I want to put that. It's the difference between building your own brothel and using someone else's. It's your own standards, it's your own everything, it's your own artistry, it's your own property, it's your own, all of the crazy sort of comes out because you're not using someone else's. So when you're the employee engineer versus the owner engineer, the equipment that you have available limits you to what you're able to do. You know that these other parts and components exist, but you now have to buy into the make and manufacturing of this unit. And the buy-in on that is not horrible, but it's the educational, cost. It is the educational cost, where it takes me about 6 weeks to learn each new video. So each of these videos takes approximately 6 weeks. So it's about a week for the kit. So the week for the kit. So the kit itself is pretty quickly able to be done. It's got you can do it in a week. You can do it in a week comfortably. There's 25 projects. A lot of them are simple. A lot of them are just sort of typing and relearning the C+ language. I'm not, and this is me. I don't come from a programming background. In the sense, I don't type in the language itself. I work at we're just going to string a bunch of if statements together and get our program up and running that way. It's simpler. It's been more enjoyable because I'm coming from a different background. gonna say like this is easy program. Yeah. An electrical engineer comes and looks at this. Yeah, this is the easiest circuit ever. But this whole thing is going to actually fit on a chip. Anyway, I'll do the second. Okay. So this is a chip. This is a circuit chip. It's sort of a little bit of a custom job. It comes from a kit from. I'm gonna say it. Say here. I'm gonna pull off the chip. VA kits, and so these are VA kits from Nightfire Electronics LLC. They're out of Florida. I haven't soldered it yet, but the circuit chip, the circuit board, the circuit basically comes ready-made as like a functioning component for like hobby shops and stuff like that. Those are the types of things that you're looking at. You want to get into this type of stuff. It's user interface electronics type of things. And they're accessible, just on Amazon. These guys were $10, and they set them. They'll do a custom output for you, but they're available from anywhere from 10 to 250 millivolt outputs. So that's good. And what else? And chips. You also get chips. You also get a couple of chips in this kit. They're more educational, instructional. When you get up to let's make 100 units of these things, you've already called in the circuit engineering expert to say, okay, if you're making 100 of these things, these chips, they're gonna know more about the chips that they want to use. They want stuff that's easily uploadable. So you actually can't go any further type of thing until you call in the experts here and say, this is what we've planned. How does that look in terms of now we have to make the purchases to manufacture multiple units, and they're going to look at it and they're going to be able to input all of their stuff that's sort of like, yeah, well, I can do this, and yeah, I can do that, and you kind of let them get involved and you let them do the project, but you have to have their reports and other stuff done, because they're going to say, well, this entire this fits in line here to be able to take the input from the Arduino board directly and come off of these units here. So the beautiful thing about this one is I had found this before I found the kit, and the idea here is this just takes a battery, this plus the battery plus, so it's basically my battery goes into this thing, into this board, and this board then goes in directly into the electrochemical cell, and it's all analog. There is an entirely analog system for this device. So this unit now becomes a part of the, this plus this. So the whole Joey unit is now compressed into a box the size of the electrochemical cell itself. If you want more bells and whistles, we move you up to this unit where we just, we gotta put this on the side. You make adjustments and get it reprinted and stuff like that. But it's really more sort of nailing down what is the common thread amidst all of these, and then you can say, okay, well, this is now what the manufacturer supply line looks like, because we're gonna invest more heavily in the more common things that are required than the uncommon things. So the whole the one piece of this whole entire, globalized industrial supply line is this stupid electrochemical cell has not been standardized, because there wasn't a reason to, but this is like, okay, well, how small can you get it? Like, how small do you need it? How small do you want it? That part becomes really expensive because it's not just it's not just determining the volts with the voltmeters. It's more you have to get chemical affirmations from the device based on its physical proportions. So it's very possible to get an electrochemical cell, the micro size of an electrochemical cell, to be able to do these types of drug identifications, I guess, drug activations, drug identification. There's a whole analytical side to it, but you need the analytical detector, and you need to be able to get that analytical detection technology compressed as well. It needs to go smaller. Right now, those HPLCs and GCMSs, because there is this large sort of liquid overhead, you can't get away from them not being the size of, a desktop computer. There is a console, plus the computer itself, plus the pump, plus the spectrophotometer, plus the liquid portion of it. And this all kind of goes into this thing. So it's like, well, that technology, it's like, does have micro components to it. It's just not it's not a household type of technology in that you would actually just like once you set up your laboratories, you don't really care. You don't really need that type of equipment to get very small. You'd love it to get smaller, but that just means it's going to be less. It's going to be way more engineered, which is just a lot of stuff is over-engineered. That type of stuff doesn't need to be crazy, but the point is, in order to get standard equipment and standard chips and standardized, in order to get an electrochemical cell micro-sized and standardized like some of the rest of the electronic world is, you need to be able to know why it's being standardized in the first place. And this is why the flow-through electrochemical cell is sort of being standardized. So you can get it smaller, you can change its configurations, you can make it so that it's an input and then two flats, and then an output for the liquid portion of it. It kind of makes like a little sandwich kind of thing. It kind of makes that more difficult from it makes it easier. Actually, that is the engineering easiness of it, but it gets rid of the whole teaching components, and the rest of this is I have to be able to teach and show visually to people who are coming from the medical world, not the engineering world. And that's sort of why it's just sort of like not. That's why this is the way it is. It's like there are like you can just take that electrochemical cell and then have it be like two sandwiches. It was like, here's one electrode and then here's the other electrode, and you put them together like this, and then you put the membrane in between. Super easy. So as you do this, you take your anode, your sandwich, and your cathode, and you just have it like that, right? And then you build it so that the flow comes in one half, it flows through double these, and then it pops out the other side. And then one's like a reservoir, and then one's the other one. You get like a little brick this size, and that's your electrochemical cell. But that doesn't sort of teach, and that kind of doesn't work as well with the IV flow systems, because you're already living in this larger anatomical space that is not engineered. It's a biological space. Not to say that there's not biological engineering, but it is more that you have to get this type of stuff to be able to work. this is a smaller component of their day-to-day lives. If something goes wrong with this, they're not thinking about like the engineering on it. They're actually coming in and saying, okay, well, here's all this stuff, and they themselves kind of have to be able to be independent to be able to use this and repair it, and you know, they have to clean it, they have to do their stuff, and that's basically it. They need to know how the new technology works in that really juvenile, really implicit and totally understandable way. And then, you know, 20 years, you know, 15 years down the road, then you can put everything in a magic box that says you just clip this to the IV pump, it makes 2 little punctures, a bypass comes through, and then gets fed back into it, and that's it. So that kind of works one way, and that kind of works another way, but each country is going to have their own capacity to sort of design what they want based on the functionality already provided in the free version. That's all left up to the designers. You know, you can put filigrees on this thing. You can do crown molding on. You can you have a whole entire crown molded box. You know, gem set enamels. But that's all like, you know, bells and whistles beyond the fact. Like this is a light bulb. It functions as a light bulb. The difference is, you put the water goes through the light bulb, and that's what kind of like fucks everybody over, because now they have to deal with this extra light bulb component, this extra parameter to the light bulb. There's like 3 extra parameters introduced with the light bulb itself, and it's, you know, the space requirements start getting out of control and all these other things. So that was that's sort of par for course for this thing. The whole kit itself actually gives you more than enough to build a ton of like sensors in the kit in that box. Like, so basically you can set it and forget it if you have all of the if you really just want to be an electrical engineer. Yeah, here's one of those like pissing contest kind of things. Basically put all of these sort of like components, little widgets or whatever. Put all of those components into one single functioning Joey unit. You'll be able to have operator distance so you'll be able to detect operator distance, humidity and temperature. You'll be able to control it with a keypad and a remote control, like an IR controller. You'll be able to physically lock someone out with a little servo motor. You'll be able to have a proximity alarm detector wired up, so if somebody gets too close, you can use the sonar beam to set off a light bulb and a buzzer. The buzzer term is just sort of like skipping my mind right now. But that's the buzz. That's, you know, you can cram it all into one machine and go from there. You know, put a vibrator on it and watch it walk out the door. Yeah, where to put it? I'm looking for the kit. So that's sort of the idea here. So like in this kit, you get a lot of stuff. Like you get a little keypad. Keypad works. The keypad will beep. Also, you get the keypad to beep when you use it. The remote control. Yeah, the remote control and a thing. You get. Oh, this was smart. This little one guy here. This is a. There's a proximity IR proximity detector, but the lens that's used on it. It's like a compound eye. So it's like, for me, all of this comes back to like these biological function things, and it's just like, blowing my mind, blowing my own mind here with this thing. That was something else. That was for the servo motor. There's a stepper motor too. Servo motor, stepper motor. This is the sonar thing. This is the sonar one. So that was neat. And then they gave you a joystick too. So if you manage to get that thing to the point where you can like move it up and down on the you can get that thing to walk around and drive around the hospital on its own. So that's sort of like they give you a lot here. There's a lot of like sort of depending on like if you're I bought this because I'm just starting out. I've built my own computers before. I've done maintenance on my own computers. It's just now that, okay, outside of the world of computing, there is a whole bunch of cool bits and parts of electronics. The idea is the Joey can actually just be this size. You can put the whole thing on a friggin' chip this size, and the water flows in from the front and does its electrochemical thing and spits out the back. And the whole electrochemical chip. So that's basically kind of what I'm like pushing towards almost, is that the electrochemical cell is actually capable of becoming an electrochemical chip. To be able to put it on the circuit board. The biggest thing is getting like, well, how do you do the flow lines and all that stuff. That's not too bad because they do make like microcapillaries for the HPLC. So the microcapillaries from an HPLC can, fit on this, and then it can come back out. That's sort of where it's like, well, if you're the electrical engineers in the microsciences and the microchips kind of world, this is something that you would like really want to look at, because now you're getting into like micro fuel cell sort of creation. So it's like if you can get a fuel cell this big to be able to produce enough hydrogen for a small like robot, or for a cell phone, or for the point is you can have, but you can like you're not stuck on solar. You can go out into the bush, you can fill up a cup and power your radio system on a cloudy day from the rainwater without it like turning into a fucking indoor, because that was stupid. But the whole point is, there is energy available that you can like, make products of and sell. So that was cool. This was cool too. There's a build your own Pong in here from the Arduino program. It comes ready made. The whole idea is here to show you, once you do the whole tutorial, it brings you back to say, okay, well let's speed you up. Here's some pre-typed stuff. Already kind of ready to go, but it's demonstrating for you where and how a thumbstick controller, because a thumbstick controller is two of these in essence. So it's like, okay, well, how did the people in the 60s make Pong the first time so that it was deployable in 1972? That's kind of the idea here, where if you can change the voltage to make an oscilloscope, you can make a better program to make a better Pong, basically. And then they also give you a snake with the same sort of idea, where you turn the knob, you turn the voltage on the knob. The voltage on the knob then is able to, move something, because it's like the amount of electricity you put something, either lifts it or doesn't lift it. So it introduces you to how electricity works and how these electronic pieces work. I try, like, honestly, the first thing I'm thinking of is like, how do these components get integrated with the electrochemical cell? Because finding the electrochemical cell that can do organic molecular stuff is now, it's like, okay, well, let's put a control, like, let's put the potentiostat in front of it, and then hook up another one and just treat them as two light bulbs in series. So now I can manufacture steroid hormones, or now I can start decomposing organic pollutants in wastewater streams. I can set one to this. I can have one pre-treatment here, and it can cascade and overflow into a different reactor with a different material at a different voltage to be able to continue digesting stuff. So that's sort of like how your different enzymes work in your body. So first off, you start acidic in your stomach, and then that goes through your, you get your you get your pepsin. Your pancreas gets involved and dumps that into your small intestine with bile, and then that goes down. That goes through the whole thing, and you're getting all these different you're getting these different enzymes through the chromatography of your gut lumen, doing different things at different times. So you can make and model an artificial gut with this type of equipment. Just changing the pH values or changing the materials that you're using to hook this whole thing up. But you can do it with these little micro light bulbs. So now you get these little micro electro chemical light bulbs that are sort of lining the inside of a ring, so that as the digestion passes through it, they're able to break stuff down for you and then let the body absorb it that way. So, you can get an artificial gut out of the whole thing. That's sort of where innovative potential kind of goes ape shit, basically, is that you're able to get these micro, it's just a step beyond lab on a chip, because you now have to get that lab on a chip implantable and for purpose without interfacing directly with the enzymes themselves. So it really just is kind of like this, it's not even sci-fi, it's just more it's like proteins are your new electrical components, and how you put them into electrical series based on the structure and shape of, it's like you can get a green light bulb, you can get a blue light bulb, you can get a red light bulb, you can get protein A, protein B, protein C, or enzyme A, enzyme B, enzyme C, encoded in these light bulbs, and that's how it works. That's how the real world is now operating. This is where we're at. It's getting that manufacturing supply line up so that you can get these some poor fellow got, I don't know, a disease, we'll say a disease or something where you can't, it'd be like putting a lactase implant in. At what voltage does lactose break down? Can you keep it clean? And can you do stuff? I don't have to do it to GMO pathway. I can just implant you with a little electrode, stick it up your ass, and stick this up your ass. Anyway, we'll get better at it, but we'll stick this up your ass so you can digest lactose now. We'll wire it into a nerve, we'll hook it with a nerve, and it just stays there, digesting lactose for you, so you don't have to have the shits. But it's doing all the front end work for the lactase light bulb. That's where the HPLC in comes in. That's where all of the other work done is sort of already done. So there are linear sweet voltammetry for lactase has a maximum peak at 1 volt, or something like that. Go look it up. So that means your light bulb has to go at 1 volt, and it has to have a filtration membrane on top of it to select for molecules of that size. That is totally viable. That is what this thing does right here. That's how this is so fucking important. So that's sort of it. it's about 6 weeks worth of stuff. It's summer now. I cut my hair. COVID's over with. I'm happy with what I learned about COVID, so I don't need to have the hair anymore. I miss it. Not really miss it. It's just more of like, it's 3 years worth of growth, and you know, you kind of do it every day. You shower, you wash it, you take care of it. You every comb and brush stroke through it. It's just like, you know, you feel it picking on your head, kind of thing. From that point on, you just sort of keep building and keep working on it, because eventually at some point the whole thing, like this whole thing is basically, it needs the finishing touches that, okay, if I have to sit down and do this myself, this whole circuit board, like this whole circuit board can be integrated into an actual integrated circuit board. So this whole circuit can be put into an integrated circuit board and then printed, and then that saves everybody's time, because now all you have to do is power supply with the circuit board, and so the whole Arduino board can actually be like simplified further once you know what's going on with it. That's sort of the whole idea on this stupid educational like strip we're on right now, is that you have to get the simplification. So your Arduino board gets stripped down to just the bare circuitry required. That's kind of what this is for. Like, once we figured out what we can do, okay, well, this kit is available. Solder it together, get it up, test it, see what it does, and then compress the cube. Even, your car has been crushed into a cube. Your cube has been crushed into an even smaller cube, and we're kind of almost ready to go with that, because it's handheld. It's not handheld. It's not the IV unit. It still is the IV unit, but the IV unit now is handheld. So can you get all of the redundant, like, to not be like super expensive or super obsessed about it? It's just, can you get the 6x6x6 box into a 3x3x3 box? Because that is with all of the with literally all the light bulbs and bells and whistles and redundancy worked in, or does that just like stop at, because the physical circuit size is that large? So is it just like, okay, well, we'll just stop at like 4x4 box, 4x4 cube, and it does the whole thing in there, and that's kind of, you're finished, and then that's where it's just like, okay, well, wait around, build another one, see how that goes, work on the program, on sort of what it's doing, how it's feedbacking is, and are you able to push the requirements like the whole idea here is to keep it functional, because if you go further, the system will do other stuff. So you don't want it to do other stuff. You keep it low voltage like this. You keep, there's 1,000 like, the safety protocols and all this, and like what happens if this, like, that's part of the like, okay, shut up. When you have 10,000 or 100,000 people working on it or using it, yeah, their problems will come up, because you just throw shit at a fan, you're gonna get splatters everywhere. But right now, everything's clean. So that's sort of the idea with like FDA approvals and stuff like that, where it's like, well, they want you to provide this type of like redundancy thinking pattern for other people, because it's like, well, when that kind of goes into production, it's like, okay, well, be aware of this. If you spill this stuff, what happens? How do you know there's a spill? It's like, well, why is there a spill in the first place? How did you even spill it? Did you not assemble the apparatus correctly? Because if you do everything right, nothing goes wrong. Hey, only goes wrong if the user operator fucks up somehow. So that's sort of like the real idea here, where it's just like, okay, well, everything fucked up and we have to do extra stuff, and extra stuff has to be done, and the FDA wants a ton of that stuff. It's just like, well, think for me, because I don't have to think. And it's just like, well, turn it around. And same with Health Canada, same with Europe. They want to know, like, okay, well, what can possibly go wrong before we start using it? And it's just like, well, your instructor operator didn't read the instruction manuals and just thought they were going to do whatever. But then it's like, you turn around, it's like, no, there are red herrings, and you have to operate it in a certain, or there is an order of operations to turn it on. There's a preferred sort of SOP. 1, you read the SOP. 2, you follow the SOP. 3, you decommission according to the SOP. 4, if there is some sort of like component manufacture, so you're there's enough, like, you're getting into a lot here, but the whole entirety of the country has already been mapped out. So who cares about the lot when you have the entire rest of the country to play with? That's sort of how it goes here, and then you get the other country to play. Like, so you have the entire world to play with, but at the same time you're still like super focused on this stupid lot, because that stupid lot is like the gateway to getting those safety regulatory approvals, where it's just like, okay, well, short of the person just not being like fucking stupid and, you know, doing a football spike into the ground with the damn machine and then try to operate it afterwards, you know, you mix your drugs, you mix your solution, you put it in the top, you fill it up, you put the lid on, you close it up, you put it on with the rest of the flow line stuff if you're going to do a flow line. You open the spigot after it's set time. It's going to drip into another cup. Make sure the cup is there. Like one of those automatic coffee pod maker things for drugs. It's the same idea. It's gonna you put your stuff in the top. It's gonna do some stuff. It's gonna spit it out the bottom. Make sure you have a coffee cup there. Otherwise, just piss, hot coffee everywhere. Make sure it has power, and go from there. This has been out in the sun for an hour already, so you can do the surgery outside. No, you can't do the surgery outside. It's that old Dr. Hibbert thing from The Simpsons. But that's the whole thing. That's the whole idea here, where it's like, okay, well, this is all well and good. Your doctor doesn't typically have the electronics to make it. Your oncologist is not an electronics expert by any means, or are they expected to be? But you're not getting this piece of equipment used on you unless they start becoming one. So that's sort of where we leave you off at the hour. Clean everything up, make sure it all works. All of this other stuff is good working condition. Good working conditions. Get some control over everything, and it changes it. You get different pieces, and you get different parts of, like, how intelligent do you want to be with this thing. And after a certain point, it does kind of just boil into design and artistry. That really sort of moves. That's where the marketing comes in. It's just like, well, what does this look like? This is where it's like, well, if this is about the size of it, yeah, well, it's going to be able to fit in a little water pistol type of thing, because I'm going to be able to do this multiple times. The water's going to jiggle around, but it's all sealed, and that's sort of there's your cancer gun. This is where the cancer gun comes from. So this can now get, this can now get put on a robot arm, and the robot arm with the the robot surgeon can now come in and do it that way. So this is a probe for a robot arm. This is also now the beginning of a probe for an auto sampler kind of thing. The Opentron by Opentrons is basically stick this little apparatus on top of your Opentron robots, and now you're able to do your lab on a chip stuff. So so the situation is extremely amenable to actually being able to help a lot of people with limited resources and being able to do something that's already been done. But you have to get the other corporations to comply with the invention's purposes and the invention's obligations and requirements for, some like actual serious investigation. Like, back to the masters, open up the masters, and make sure your new medical devices adheres to the original masters. Because those protocols and that equipment has already been approved by a lot of people. So each iteration of the machine, like those are your standard operating procedure. That is your standard operating procedure for each medical device. Happy, we're all happy. That's our little show for the evening. If you're just tuning in, we're tuning out. There's not too much else to do. Nightfire Electronics, thank you. If you're interested at all in soldering, pick up a soldering gun. Get the rosin core. Get the. Yeah. Okay. There you go. From the Tox perspective, this was the best one. It was Okay. This is the Enersystic lead-free solder wire. It's a rosin core with a 2.5% flux, and it's tin silver copper. That's the solder I used. That's the one I picked out. From the Tox perspective, it's lead-free. Try and get lead-free, particularly when you end up with the smoke. Okay, so that was the thing. If you have to use lead-free, get one of those little pocket fans from like the dollar store and set it in front of what you're doing, because when the rosin burns and when you get those smoke puffs, the impulse is to actually just breathe in the smoke, but you're getting these burnt out ionized lead particles kind of going into your nose and into your face and stuff. It's just more of blow it away first, or do learn like a little breathing technique where you breathe out while you're soldering and applying the solder, and to blow that smoke away. But you really should have that little pocket fan there just to keep it cooling, just to blow that smoke out of your face, because it goes like you look in at the tip, and you just breathe in. It's the impulse is to breathe in the smoke, because it's like a barbecue. It's like a barbecue mentality. It's working with fire stuff, so it's like cooking. You want to breathe in the smell to know you're cooking well, but when you breathe in that smell, you're getting whatever's coming off of the stuff. So it's basically blow the smoke away. Hot soup and spoon, blow it while it's cooling and you're soldering, and that smoke just kind of goes away. So you gotta master your own little technique there. But those dollar store fans, you turn one on and it just blows across your workspace. That's sort of the best as anyone can do, unless you get one of those like elephant trunks, you know. And oh yeah, that was a cool. Oh yeah, that was a cool one. The idea here we went with that kind of popped up to us was the it's a gel electrophoresis, but gel electrophoresis using carbon nanoparticles to be able to build your own circuit boards, kind of thing. So you put the components in the gel and then run the current through the gel so that the nanowires sort of align along the electrical field gradient in the gel itself, and then forms the electrical circuit for you. And that way, that's the path of least resistance between different components. And then you'd either sort of like laser scintillate those together or run an actual voltage through it so that the particles would anneal into a microwire, and just sort of repeat the process until you get what you want. So with that, you can kind of get into like 3D printed 3D circuits. So you can get 3D circuits and out of it where you can just sort of like keep layering on top of components and stuff like that. So the idea there was like you'd have like a graphite so you have your 3D printer, but then you'd have a graphite goo, and you'd laser weld your circuitry together with the components in the goo because it's more of a gel. So there's a couple of little babysitting things to work out. So you'd form a 3D matrix through a laser printed shape, and then as it's being printed, you'd have to stop it, put your piece in, and then continue like building the goo around it. So that's not impossible to do, but it is its whole own, you know, technique, whatever you want to use it for. There's that one, and then there was the there's like laser scintillated circuit board creation, and then there was the carbon nanotube gel electrophoresis circuit board technology that kind of got intercepted when I was learning how. When I was turning into like bitch fest for soldering, it was like, well, you kind of implicitly learn how all of these other like microchips are made. It's like, well, the first person who had to do this back in the 1940s or whatever, or the 30s, probably the 20s, maybe even sooner, was just basically like, well, I'm sitting down and doing this, my neck is sore, my back is sore. First thing I want to do is build the robot to, you know, so I don't have to. First thing I want to do is build a machine to not have to ever do this again. And these are two techniques that I had kind of come across with, like, you know, how do you lay, like, when a protein or a piece of DNA goes through these gels, there's a size exclusion capacity, so you can automatically set up a gel with different densities, so you can go from agar to SDS page kind of thing, and set up these different filaments. You're just basically running these carbon filaments through a gel under a path of least resistance and creating your circuit that way. Just so that you're just gonna, like, you basically, here's your gel and here's your component, you stick it in, and then, I don't know, you can laser it or scintillate it or do something to just polymerize the gel or wash the gel off, so you can get like a little microfilm of nanoparticles, and now you're really into some kind of like cool manufacturing here, where it's like, no, here's our SDS page gel with nanoparticles in it, and we're able to run it as a computer chip or something. We're able to light a light bulb with it because the whole gel is now like, you know, the Star Trek gel packs or whatever. This is what they're made out of, basically. Carbon nanofire version SDS page. So this is still on. You can shut it off. So the runtime on here has been 50 minutes, and that's it. Arduino program basically data logs everything. So the idea here is, like, if you really want to kind of do this, is you get a data log, and the data log then it has a Wi-Fi component. Like if you really wanted to build this whole thing up, the Joey comes with a data logger for knowing if there's a failure. The data log can get uploaded to a server database system that's just going to storage all the storage and record the times of usages, just for insurance purposes, so that you can know if it was a faulty equipment, a faulty device, if it was an operator error, if there was like a proximity control. Did the user bump it? We could put a little spoiler on it. And just that. And for me, that's data for the sake of data. But that's just me talking because I've done enough. I'm tired, and that show's over. But that's sort of like kind of where we go with this, where it's just like, okay, well, all these other ideas come up, just trying to get out of doing work. That end up being, somewhere down the road they will become useful, but they're said here first, so fuck your patent. Fuck your patent, I said it first. But that's sort of the thing where it's just like, okay, well, those types of things are or were probably or possibly considered, back in the 40s when they were building the first robots, because it's like, you're gonna have to make 1 billion of these stupid fucking microchips. Now they're just like laser and microscope set, but it's like the first thing you do if you want to make them smaller, you put a microscope in front of your face and you do the soldering that way. That's sort of like what the idea here is like, okay, well, in not having the microscope, the first thing you want is a microscope. In having the microscope and not having the lasers solder gun, the first thing you want is a laser solder gun. So it's just like, okay, yeah, well, today everything's done by a super ultra high powered laser, and that's your answer. But you managed to close a century worth of industrial development with 8 million people. How and where does it apply to this? I don't know. Well, I do, but I don't know where. Sometimes smaller isn't, like, you do a whole fantastic voyage with this on a microchip or something, but it's like, why? Like, you can operate. Just go back to the fucking porphyrin and go from there. That's what it is. That's how it works. That's the end of it, and that's the end of our show. So that's stuff. That's our stuff segment from the world of innovative potential. Actually, it's more of our